Hello everyone, I am Angelo Borja with my group mates Miss Czarina from Mariscal and Mr. Akiah Gonzales. We're students studying BS Electronics Engineering in Bicol State College of Applied Sciences and Technology. We expect that by the end of this video, we will learn about the impulse train signal. I will start by defining what is an impulse train signal. An impulse train signal is a repetitive series of pulses separated by time by a fixed and often constant interval. The duration of each pulses and its amplitude are also often made constant. This type of waveform may be defined by its Mark space ratio, that is the ratio of pulse duration T1 to pulse separation T2. With this statement, where each pulse and its amplitude are often made constant, means that all the impulses have constant amplitude until it's or up to infinity. It means that up to from negative infinity until the positive infinity, the amplitude will always be 1 or depends on what is given. This also means that the interval between two pulses also is constant. It means that if the interval is 1 second, the interval between here and this impulse is the same. As it goes by, it is still the same from negative infinity to positive infinity. Next is the impulse train signal equation. Impulse train signal equation is denoted by P of tau of t is equals to the summation of Dirac delta function t minus k tau from k is equals to negative infinity to positive infinity. If the pulse defined by the function is separated every interval t, a periodic waveform results with a period of t and repetition frequency of f is equals to 1 over tau. The Dirac delta function is one example of what is known as a generalized function, or a distribution. Paul Dirac had introduced this function in the 1930s in his study of quantum mechanics as a useful tool. It was later studied in a general theory of distributions and found to be more than a simple tool used by physicists. The Dirac delta function, as any distribution, only makes sense under an integral. According to this statement, it only makes sense under an integral. So, this Dirac delta function would not make sense if the function is not within an integral. For the impulse train signal, the function is within this summation from negative infinity to positive infinity. T is time, k is any real number, and tau is the period. This part of the equation means that time is delayed by a certain time. So if tau is 1 second, the whole impulse train signal has the period 1 second. K is the number or harmonic number that will define what part of the graph it is. For example, if this is 0, if k is 1, the impulse function will be here, or only it means tau or the period. And based on what I said, if the period is 1, this will be 1 second. Tau, by the way, is in seconds. Next is the Fourier series of the impulse train function. We have three forms: the exponential form, trigonometric form, combined trigonometric form. For the exponential form, this shows the derivation of impulse train functions Fourier series in exponential form. As we know, the general form of exponential Fourier series is in this form. The summation of c of n e raised to jn wo, or the omega naught t, from n is equals to negative infinity to positive infinity. To get the Fourier formula or the Fourier coefficient of a certain function, we will get the coefficient C of n. C of n is equals to 1 over tau, integral of the function. The function in this example is the impulse train function p of tau of t multiplied by e raised to j n omega naught t dt from 0 to t or tau. If we substitute the formula or equation of the impulse train function, it will become like this, which is 1 over tau integral of summation of Dirac delta t minus k of tau multiplied by e raised to j negative j and omega naught t dt from 0 to tau. As you can see here, the C of n will become 1 over tau e raised to jn omega naught times 0. So why did it become 0? According to this, or why did it become like this first? The integral became like this. So according to this statement, the Dirac delta function has a shifting property where the integral of the Dirac delta t minus a multiplied by a function of t dt from negative infinity to positive infinity will result to f of a. It means that this part of the equation of the Dirac delta will replace the t in the function of t. So if this is our a, if this is a, this will replace t in this part of the equation. This means that it will become e raised to negative j and omega naught kt. On the other hand, according to this statement, y t is equals to 0. Impulse train signal only focuses on the signal exactly at t or tau, where t is equals to 0. It's true for every period. This means that t, since tau is dependent on t, kt will also become 0, or the whole part of this will become 0, because when t is equals to 0, that is the time when the Dirac delta function will have a value of 1 or anything besides 0. So substituting 0, we get this e raised to j and omega naught times 0, and this part of the equation becomes 1, and the remaining will become 1 over tau. So the final form of the Fourier series of impulse train signal in exponential form is equal to 1 over tau summation of e raised to j and omega naught t from n is equals to negative infinity to positive infinity. We simulated this Fourier series in MATLAB using the code. This code is used in this graph. So as we can see here, the graph at lower harmonics, harmonic number, or the k or the n. By the way, k is also the same as n based on what is given or what is taught. So this part, k is equals to 10. If k is equals to 10, so the limits of the summation will be from negative 10 to positive 10. This will be the graph of the periodic impulse train function. As you can see, the graph looks like a sine wave with sudden increase of amplitude every period that has constant interval and also constant amplitude. As we increase the harmonic number, in this part the harmonic number is increased to 50, so the limits become from negative 50 to positive 50. As you can see, the impulses become more small, become more thinner, or looks like less of a sine wave, look like an impulse train, an actual impulse train function or signal. As you increase this to 100, the function becomes like this. It becomes thinner, more thinner, or more look like an impulse train signal. As you can see here, if the harmonic number is equals to -1, the function or the graph looks like a sine wave. As you can see here, the ideal impulse train function or the ideal impulse train looks like this. The Fourier approximation is this. As you can see, this isn't our ideal impulse train signal when the harmonic number is low. Next is the trigonometric form of the impulse train signal. This shows the derivation of impulse train functions Fourier series in trigonometric form. The general form of trigonometric Fourier series is this: A naught plus summation of a of n cosine n omega naught t plus b of n sine n omega naught t from n is equals to 1 to positive infinity. To get the first coefficient a naught, which is equal to 1 over tau integral of the function or the equation of the signal times dt from 0 to tau. The second coefficient a of n is found using this formula 2 over tau integral of the function cosine n omega naught t dt from 0 to positive tau. B of n, or the third coefficient, is found using 2 over tau integral of the function sine omega naught t dt from 0 to tau. If we replace the equation of the impulse train signal, a naught will look like this. And according to the property of an Dirac delta function, the integral of a Dirac delta function will always be 1, will always be equal to 1. As you can see here in this statement, the integral of the Dirac delta function over an interval that contains its impulse is 1. This is also because in the impulse train signal, the focus of the function is only when t is equals to 0, and the integral of the Dirac delta function at t is equals to 0 or t is equals to kt is 1. The Dirac delta function is 0 everywhere except a single point, but its total integral is always 1. As you can see, this part of the equation will be equal to 1. That's why a of naught is equals to 1 over tau. Next is the second coefficient a of n. If we replace a of n with this function, the equation of the impulse train signal, it will look like this. The shifting property is again applied here, since if the Dirac delta function is multiplied by this function cosine n omega naught t, the t will be replaced by k of tau. And also the same as the exponential form, we only focus on the 0 of time, or t is equals to 0. That's why t becomes 0 in this part. So this part will become 0, and cosine of 0 is always 1. This means that a of n will equal to 2 raised 2 over tau. The third coefficient is equals to this. This means that we again apply the shifting property on the sine and omega naught t. Once the shifting property is applied, and the same property such as the t is equals to 0, b of n becomes 0. Substituting this coefficient, the found coefficients a of naught, a of n, and b of n, the exponent or trigonometric form of the impulse train signal is this: 1 over tau plus 2 over tau summation of cosine and omega naught t from n is equals to 1 to infinity. As you can see here, this is also used in simulating in the MATLAB using this code. As you can see, the graph looks similar to the exponential form. This means that even though the form of Fourier series is different, the graph will result to the same visual. As you can see, the harmonic number 10 is the same as the exponential form until the harmonic number 50, it is also the same. Again, it is the same as the exponential form even if we use the trigonometric Fourier series in this part. Finally is the combined trigonometric form of the impulse train signal. It shows the derivation of the impulse train functions Fourier series in exponential form. Both have similar formula and solution from the previous types of the Fourier series since the this means the C of k, or the coefficient C of k, or the absolute value of C of k, have a number value of a real and a positive number, then it is equals to 1 over tau. It is because it is already constant and does not have any variable or anything that makes this different. Since C of k has no imaginary component, the angle or the theta k is equals to 0. The result is the same as the trigonometric form of the impulse train signal Fourier series. Again, it is the same as the exponential form and trigonometric form on different harmonics. This will only represent the harmonic number based on its value. As we increase the number of harmonic or the harmonic number, the graph becomes more look like an ideal impulse train function or a signal.
Transformations of discrete time signals. Discrete time signals transformations are operations that modify a signal's shape, timing, or amplitude without changing its essential identity. These transformations are essential in signal processing, communications, audio and video engineering, and lastly, control systems. The first transformation that will be discussed is the time reversal. The time reversal transformed signal y of t of x of t is obtained by replacing t with negative t in the original signal x of t. That is, y of t is equals to x of negative t. The graph of the time reverse signal y of t is the mirror image. Playing music on the CD backwards is an example of time reversal. A common example is playing music in reverse, where the sound order is flipped. The last note plays first, and the first note plays last. Now for the code and output. In this code, we simulate a discrete time signal and perform a time reversal. We start with the time values from negative 5 to 5 and amplitudes from 0 to 1. To reverse the signal in time, we reverse both the amplitude array and the time array, flipping the entire signal. As a result, our output shows a mirrored version of the original signal, demonstrating the concept of the y of t that is equals to x of negative t. This matches our definition. The signal values are unchanged, but they now appear at the opposite time positions. Now for the time scaling. Time scaling. A time-scaled version of x of t is y of t equals x of at, where a is a real constant. Now, if the absolute value of a is greater than 1, it means compression in time. It means time passes faster. The signal becomes compressed and events happen more quickly. Now, if the absolute value of a is less than 1, it means expansion in time, and time passes more slowly. The signal expands and events are stretched out over a longer period of time. A real-life example of time scaling. When you listen to an answering machine message on a fast forward, you can hear the voice pitch. Frequency content of the speaker's voice is increased. This is due to speeding up the signal in time. It only happens because the signal is compressed. More information is played in less minute. For the next example, when you play a 45 revolutions per minute, 45 RPM analog recording at 33 RPM, you can hear the voice pitch. When a 45 RPM vinyl record is played at 33 RPM, the music sounds lower and deeper. The signal is expanded in time. It takes longer for the signal events to play. Now for the code and output. This code simulates the effect of time scaling on a signal. We use a signal that rises from 0 to 1 between t is equals to -5 and t is equals to 5. When we apply a is equals to 2, the signal becomes compressed, fewer values over time. When we apply a is equals to 0 to 5, 0.5, we get more time points. The signal stretch out. The shape remains the same. We're just changing the speed at which it's played back. Now for the time shifting. Time shifting. A time-shifted version of x of t is y of t equals x of t minus t sub 0, where t sub 0 is a constant. When t sub 0 is greater than 0, it means delayed in time. When t sub 0 is less than 0, it means advanced in time. The graph of time-shifted signals t sub 0 is equals to 2 and t sub 0 is equals to -1 may seem counterintuitive. Think about where the t minus t sub 0 is 0. Now in this code, we simulate time shifting using a signal that gradually increases. First, we delay it by 2 units by shifting the time axis to the right. Then we advance it by 1 unit by shifting the time axis to the left. As you can see from the plots, the signal's shape remains the same, only its position and time changes. This demonstrated the principle t sub 0 greater than 0 delayed and t sub 0 that is less than 0 is advanced. Amplitude scaling. It changes the magnitude of the signal without altering its time behavior, where x of t is a multiplied by x of t, where a is a constant. So when the absolute value of a is greater than 1, it amplifies the signal. But when the absolute value of a is less than 1, it attenuates the signal. Applications of amplitude scaling is volume control, signal gain adjustment, data normalization. Amplitude scaling means you're multiplying the signal by a constant factor. This changes how big or small the signal appears, but it doesn't affect when the signal happens or its overall shape. Think of it like turning the volume knob up or down. You're not changing the music, just how loud it sounds. So for the code, we used a simple signal and apply amplitude scaling. The red plot shows the signal amplified by a factor of 2. You can see how it stretched vertically. The blue plot shows the signal attenuated to half its size. Time remains the same in all plots. We're only changing the vertical scale. This demonstrates how amplitude scaling can make a signal stronger or weaker, a key concept in systems like audio, electronics, and data processing. Now for the last transformation, amplitude shifting. Adds or subtracts a constant value to the entire signal, shifting it up or down. Where x of t is x of t plus k, where k is a constant. Now the effect of amplitude shifting, signal moves vertically without changing shape or size. And one of its applications is setting a DC offset, signal level adjustment, and preparing signals for analog to digital conversion. For the code, this example shows amplitude shifting in action. We use a signal that smoothly rises from -1 to 1. When we add 1 to the whole signal, it shifts up. The peak moves from 1 to 2. When we subtract 1, it shifts down. The lowest point becomes -2. So if you notice, the timing and shape are not affected. We're only moving the entire waveform vertically. This is helpful when preparing a signal for analog to digital conversion or adjusting its baseline for processing.
Hello guys, this part will be the simulation of impulse train using MATLAB Simulink. Now this simulation circuit has 6 parts: the pulse signal, the delay, the adder, the constant, and the switch. Lastly, the output will be shown in this oscilloscope. Now, in the signal generator, the pulse must be set in square wave, amplitude 1, and the frequency is 1. The delay, we're gonna set it delay length in 0. And the adder must be set in positive and negative. And the constant must be set in 0. Then it will go through the switch. Now let's test the simulation circuit. The output shows a impulse train signal which describes same spacing between the spikes and the narrow signal width. Now in this part of the video, we're gonna talk about how does every part of the simulation circuit works. Now the pulse generator will send a signal to the positive side of the adder and 1 to the delay. As shown indicated in the arrow, a picture above shows the square wave and the delay. Now, what's the purpose of this adder? It will subtract the square wave and the delay, and the output becomes like this, as shown at the bottom picture. Now, the signal will go to the switch. Now, what's the purpose of the switch? The switch blocks passes one of 2 inputs to the output based on a condition applied to a third input. As shown, the block has a constant of 0 that applied to the third input. It will remove all the signal from 0 below. and the remainings are this positive side of the impulse train. In this part of the video, we're gonna talk about the impulse train applied in MATLAB GUI. Here, we made the amplitude and frequency set in 5 and 10, but editors can change it. Now, every run button have significant or specialized code for each role. This is the run for amplitude and frequency, and this is the code for 6 transformation, although we made it 5 because time reversal are absolute in impulse train. Now let's test it. As you can see, we can access the user interface in GUI MATLAB. Let's run, and it shows an impulse train with amplitude of 5 and a frequency of 10. Let's change the time shift. Now it shifts from 0 to 1 to 0 to -1. How about the time scale? Let's set it about 0.5. And the impulse train squeezes about 50%. Next is amplitude shift. Now it shifts from amplitude of 0 to 5, and the amplitude shift added 2, so it becomes 7. The amplitude becomes 7. How about the amplitude scale? Set it in 2. Now the amplitude is 5, and now it becomes 10. So 2 times 5 is 10. The amplitude becomes 10, and when you amplitude reverse it, it goes to negative side, which is -10.